Okay, we are on one of our last theories, the planet migration theory, and we're going to hope that this looks at the planetary types and the sizes that nobody else can explain, and some of the space debris issues, because we're still not sure about what's going on with the asteroid belt, and the common age problem where accretion happens slowly and gas collapse happens fast. So we've got this other theory, planet migration theory, and we're going to find out if this satisfies the characteristics, and then we're going to compare these theories to what we know of other solar systems beyond our own. So when it comes to these theories for planetary migration, we're trying to see if it can explain why Mars is so small and why Uranus and Neptune are relatively small compared to the other Jovian planets. And we're trying to explain the odd elliptical orbits of the Kuiper Belt, sending in comets at very strange angles, and this disparity between the accretion models and the gas collapse models in terms of age of the solar system. Now, you've seen this visual before, and it refers to a theory of planetary migration. This theory has several different models in it, or several different hypotheses. The grand tack hypothesis is the easiest one to understand, so I wanted to show this to you again. It's called the grand tack because it's named after a sailing move. And here's the thing. So a sailing move, when you have the wind coming at you, means that you have to, quote, tack into the wind, and you have to go one direction and then turn around and go another direction. You have to go, if the wind is coming at you from the north, you have to tack your sails to go east, then you have to tack your sails to go west, and you go and you make moves north against the wind. That's called tacking. In the same way, the Jupiter especially goes toward the sun and then retreats and goes away from the sun. It seems very strange, so we call it tacking because it's making these directly opposite moves in the middle of this migration. Why did it migrate? Well, here is year zero when the protoplanetary disk forms and Jupiter starts to form first. A big part of the theory of planetary migration is that the gas giants formed first. Not everything forming together with the terrestrial planets. It was the gas giants in this theory. And Jupiter formed first and gained gravity and was able to pull in a lot of dust. When it gained some gravity, it was pulled in and gained so much mass, it was pulled in by the sun. So it started migrating closer to the sun. The sun is over here. As it migrated closer to the sun, it started to push all of these condensed rocks together. And then it draws in Saturn with it. So Saturn starts to head toward the sun, and they both really start to smush these condensed rocks into a smaller area closer to the sun. Well, as that happened, Saturn, the theory goes, pulled Jupiter back out again. Saturn, along with the other gas giants, pulled Jupiter back out. Like I said, it's a theory. And as Jupiter heads back out, it pushes the other gas giants in front of it. In pushing the other gas giants in front of it, a lot of the debris goes with Neptune and could possibly form that Kuiper belt out in front of Neptune. That's a possibility. And in that migration out again, Jupiter takes a lot of stuff with it, so that when the terrestrial planets start to form, there's not very much stuff for Mars to deal in. So Mars doesn't have as much to accrete, and Mars stays smaller than Earth because Jupiter's gravity has pulled a lot of dust with it. Now that could explain Mars's small size, but it doesn't really explain Neptune and Jupiter's small size. So we've got an explanation for Mars, and we also have an explanation that narrows out this difference between accretion and gas collapse. And basically it says that the gas collapse happened first and the accretion happened second. And so the timeline of formation gets a little disheveled, still not really well explained by this theory, but it does explain the Kuiper belt pretty well. Now, what do other solar systems teach us? Other solar systems, like what we see for the star Fomalhaut near Pegasus, we see that disk. And if we look at in the southern hemisphere, we can see Beta Pictoris in the constellation Pictor, and look at that beautiful disk. So when it comes to the characteristics of our solar system, of the disk shape, the different types of planets, the space debris, the common age, at least we're seeing the disk shape on visual for other solar systems. And when we look at infrared, we start to see different types of planets in other solar systems. Again, this is Beta Pictoris, and you start to see a secondary plane there, an ecliptic there, much like ours, much like our ecliptic is just about 6 degrees off of a equatorial plane for our solar system. You also start to see some differentiation here in different types of planets that can form. You see some different types of action here versus the inner area around the sun. This is actually a mask that is put by the telescope in over the star so you can see the gases around that other solar system a little bit better. Because these are so far away. So other solar systems are showing the disk shape and possibly different types of planets. Other solar systems have shown to us different types of planets. Here they are related to the size of the Earth and the size of Neptune. And so we do have other planets that we've seen. And in fact, we can notice other planets by looking for them in 2 ways. One of them is when they are precessing or wobbling due to the gravity of another planet that's near them, or even a star that's near them. So some planets are discovered when they wobble, when they get closer to their star and farther away, and it impacts their velocity, which we know about from Doppler shift now, that has planets moving toward us and planets moving away from us at different speeds. Now you know about that. This is a very complicated system where this star is being pulled by several different planets, much like a dog walker is being pulled by several different dogs. Kind of interesting that Neil deGrasse Tyson used the same dog metaphor when we started this whole semester. Another way we can discover planets in other solar systems is by watching them transit the star in the other solar system. When a planet transits a star, the intensity of the light of that star will dip. And we can note that in visual and in infrared. And yeah, in UV too, we can note that. So when you see a dip in intensity of light, that may be due to a transiting planet. We have noticed many, you saw some of the planets before, we have noticed many planets and their orbits. We're in the hundreds now for extrasolar planets. And when we look at these planets, we can look at them on a graph of distance from their sun, and we can look at it by mass because we can tell mass by this Doppler shift. And when we look at mass, what becomes pretty interesting is we can compare it to our cooler Earth and our very cool Jupiter, and we see that there are a lot of very close planets in the extrasolar regions that are very close to their sun at a very high mass. So they're close to the sun, they're at a very high mass. These would be very hot planets near a star. We refer to this sector of these extrasolar planets as hot Jupiters. And they're very different. Hot Jupiters are big, hot, close planets. And we don't see that in our solar system. We see small hot planets like Mercury and small hot planets like Venus and like Earth. We don't see large hot planets. But maybe it's because the larger planets are easier to detect than the smaller planets. Or maybe it's because these hot Jupiters in this sector haven't migrated out yet like our planetary migration theory says might be happening. A lot of questions on extrasolar planets. But one thing we do know is that, like Neil deGrasse Tyson said, your body is made up of atoms that were formed billions of years ago with the formation of the universe. These atoms were cooked by stars, and in fact, a very good representation of that is iron. It's absolutely essential for your body, and it is really very rare in nuclear fusion by the sun because the sun is hot enough to make iron, but not lots of it. This iron that we have in our bodies and in our that comes from our soil on Earth is from nuclear fusion and hotter supernovae and hotter stars. So that brings in the importance of understanding the origin of our solar system. Take a look at some of these key terms. Make sure that you can explain them to yourself, and I will see you in Chapter 9.